Okay, so let's continue talking about ideal solutions. So in the last lecture, we figured out that the change in free energy on mixing was equal to the number of moles times the gas constant times the temperature times the mole fraction of A times natural log of the mole fraction of A plus the mole fraction of B times natural log of the mole fraction of B in an ideal gas mixture. Okay, so this is interesting. It tells us that we're going to have a lowering of the free energy of mixing when we mix two ideal gases. Where is this change in free energy coming from? Right. So where does this change in free energy come from? Well, it's clear that the only place it can come from is essentially the entropy. In an ideal gas, we don't have any interactions between the atoms, so there's no real change in the energy or the enthalpy, so the only change is in the entropy. And we can see that here because we know that the partial derivative of G with respect to T at constant pressure and number of atoms is minus the entropy. And so we can take that derivative easily enough here, and so we can see that the change in entropy when we mix the gas is just minus N times R times XA natural log of XA plus XB natural log of XB. And remember, XA and XB are both positive, but they're both less than 1, so natural log of a number less than 1 is negative, so this has to be a positive number, right? So there's always a positive change in entropy when we mix two substances. And so in this particular case, we can see that delta G mixed has to equal delta H, the change in enthalpy of mixing, minus T times the change of entropy of mixing. But in this case, because we're in an ideal gas, the enthalpy of mixing is 0. Now we can simplify this a bit by noting that xb is equal to 1 minus xa, and vice versa, right? So we can write this only in terms of xa, and in that case we can write down delta G of mixing simply as nRT natural log, nRT xa natural log of xa plus 1 minus xa natural log of 1 minus xa, right? And if we were to plot that, let's put that over here, we could plot delta G of mixing as a function of xa, and what we're going to find is that we'll get, there's some 0 here, right? So we can see that if xa is 0, right, then we have a 0 here, and we have natural log of 1, which is also 0, so both terms go to 0. And the same is true if xa equals 1. And then for any other value, you get a negative number, and it's the minimum value is at xa equals a half. Right? So this is xa equals 0.5, right? And you can see that the minimum, so delta G mix, the maximum lowering of free energy we can get due to mixing is going to be equal to minus nRT natural log of 2, right? Because in that case we'd have a half natural log of a half plus a half natural log of a half would just be a half, would just be natural log of a half, which is minus natural log of 2. Okay. Now, what we do at this point, so this is just a result for the ideal gas, but this concept is generalized for all solutions, be they solid, liquid, or vapor. And what we say is that an ideal solution is a solution that behaves in this way. So that it basically has no contribution to the enthalpy from the mixing, but the change in entropy from the mixing is given by minus nr xa ln xa plus xb ln xb. And that's sort of our definition of an ideal solution. And we can see that this follows from the case where our chemical potential of A can be written as the chemical potential of the pure phase plus RT natural log of XA, and our chemical potential of B can be written as the chemical potential of pure B plus RT natural log of XB. And that is our definition of an ideal solution.